So in this video, we're going to carry on from the threads video, really, and start to talk about something very specific and mainly the reason why people get into trying to understand threads in the first place. The number one driver for wanting to know, why you need a certain thread is typically the issue with UI, that somebody spins off to a new thread, either realizing it or inadvertently, and then realizing that it states, you can't access this caller because it was created on a different thread, and basically you can't edit UI. And I showed that example in the last video on threads. But in this video, I want to, just before we go into tasks specifically and do a very, deep dive into tasks, I wanted to talk about and dig deep into this understanding of why that UI issue comes about, and specifically the thing called a single threaded apartment, which is something that the UI of Windows, specifically Win Forms and WPF, for example, have to abide by. And I'm not going to go into the reasons why they have to abide by that. I'm simply going to show you, the details of that. So we'll start by just creating a WPF app just to get some code, and then we'll compile this code and take a look at the output. So we'll see firstly that we have a fresh WPF app. Control-Shift and B to build. This should build the application. Now, if we expand into app.xaml.cs, we'll see we have a main function. We'll go to the code file first. You can see there is no main function. You go to application, and you'll also see there's no main function. So the first thing when we're trying to dig deep into this is that you'll see this main has been generated for us, because you do have, inline compiled code. The reason that's been created, and we'll take a look at that in a second, is because the properties of the app.xaml file, the build action set to application definition. So it's all default, it's all set up that way. Other pages or other windows and what have you are set to page as a build action. So this app is by default set to a special action called the application definition. That's what then decides that it's going to generate automatically, if we scroll to the top, auto-generated, it's going to generate this file for us in order to start the application. And the reason for that, as we discussed in the last video, is all EXEs, there may be some exceptions, but basically all clickable EXEs on a Windows machine typically work by having a public static main function, if you will. They work that way for as long as I can remember. So it's explicitly looking in the assembly, if you will, in the executable file, for a public static main that returns nothing. This is the entry point of the application, as it's called. So this is the very first line in your application that Windows will execute. And we can even put a breakpoint there, even though it's auto-generated code, and run and actually hit this breakpoint. And you'll see this will be the very first, and in fact, it won't let me breakpoint into that. But the point is that's your very first line of code that it comes into. And the thing in terms of importance in this video is you'll see here it's automatically added this Sta Thread Attribute. And if we step into that, there's no real documentation in there. But basically, the STA stands for Single Threaded Apartment. And the point of that is to ensure that this function, specifically because it's tagged on this function should only ever have everything in this, function itself accessed and modified by this single thread. And the point of that, again, I don't want to go into too much detail, is basically due to legacy code and COM interoperability, which is really old. So most people that are less than 30 have probably never even heard of COM, or have very little knowledge of what it is or why it is. But back in the day, you're talking when C was around, before even C++ was around, the way that things work. So the way that Windows 95, Windows 98, and going forward to this day, Windows 10 still uses COM. It still uses legacy code from early Windows code bases, as well as Microsoft Office products use their APIs as COM. But the point is that the way COM works is with a single thread, or rather the way, say, an XL API talks to a WPF application, that the cross-communication between applications or threads, if you will, happens in a very defined way, and a way that was defined many years ago and is kind of stuck in legacy. So I don't want to go into all the details of why we have to stick to one thread for the UI, but the underlying reason is because of that. And what that means is, say we chuck a control on here just for a minute, and I'll show you some legacy code in action. And we'll just do bog standard super quick click event handler. We're not bothering with any kind of mechanism here. What you could have is a file open dialog, or rather open file dialog. Okay, what's going on here? Oh, sorry. What am I doing? Oh, open file dialog. Bit too early for doing this. New open file dialog. And you can see also when we're using this open file dialog, you'll notice the namespace, clean them up, is Microsoft.win32. That's a hint that this is also legacy code. So even though it's actually part of the WPF framework, if you will, which is what presentation framework is, this is actually calling into legacy code. So the file dialog, if we step down and do a little bit of digging, we've got a common dialog, and then that's it. There's no real hint here as such. The slight hint you start getting is you can see these int pointers, which again, if you're a C# programmer or a fairly new to programming, you've probably never heard of int pointers, or you never had to deal with them, which is a good thing. But this is a way to point to specific areas in memory typically, and manage more lower level things that we don't have to worry about these days. So the hint that this is kind of legacy starts when you see things like windows and int pointers and handlers and message pumps and hook procedures. These are all legacy things. So bottom line, like I say, is this is now a legacy COM call. Ultimately, this will boil down to calling some pre-built DLL that's installed on Windows that then calls COM. So in order for that to then come back to us, when we say var result equals open file dialog dot show dialog, and we want some result, we run this file now, and we click the button. It keeps opening in this second window still. Click the big button, and then we get a browse here. So if we were to select, say, don't know, go to some random files, have we got any? Nope. Pick something from D drive. Let's go to Git, and let's just open, say, editor config. And now you see the result comes back, and it's give us true, which I shouldn't have really done. I should have then got the open file dialog dot file name. So you can see this, in order for this to populate and come back into our code, because this is calling legacy code, this has to work in COM, if you will. So if we were to not be in a single threaded department state, then this wouldn't work. So to not go too deep into this and to go off track, which is not the point of what I wanted to do here, this is just kind of a hint of where, part of the reason why we need this STA thread comes about. And it's ultimately, the single answer is, the reason that WPF and Win Forms apps need to be STA is in order to fully support anything that's in the .NET framework that will ultimately call into legacy code that we're not made aware of directly. It doesn't tell us, watch out, this is a COM object, or this needs this to behave, because by default it automatically compiles for us, makes it aware. And then as we'll dig deeper, you'll see that the application specifically that we inherit from, this application is inherently safe because it handles a dispatcher object. It's part of a dispatcher object, which then ultimately follows all the rules to make sure that we are STA thread safe, if you will. But that's not the point of where I want to go with the video. I just want you to understand that the Win Forms applications and WPF applications will be and should always be tagged with STA thread. And the reason for that is to support legacy code that the .NET framework wants to call, so it can be fully compliant. And there's kind of an example of a legacy code happening there. And that's as far as I want to go in terms of telling you why you need to do that, or why it's automatically done for you in this case. That what it ultimately means is anything on the UI thread, so any object like this button click can't be modified, as we showed in the last video, if you're not on the original thread in terms of the thread that comes about here when the application's created. So once the application's created, or specifically the UI, which should all be created on that same thread, but when you create a new object, which is done again in the initialized components automatically for us, where this is created, so this call here happens here, where all the UI gets created now, the thread that we're on here should be the only thread that then modifies that UI. And like I say, I brushed over that in the last video. So that's the reason for needing the STA thread, and a tiny bit of background without getting into too much depth. And then if you really want to dig, you can Google for STA threads or single threaded department states reasons, and you can kind of read from there. So let's talk a little bit about what it is to be STA safe, if you will. So to follow this requirement of being STA. And again, this is a brief overview and kind of to give you more of a point, not a technical document, if you will. So when other threads want to talk or access any objects like the UI elements, like the buttons, for example, in an STA thread environment, what they need to do is to queue up that message via a message queue. So they can be read when ready. Because if you have a single thread to process everything, then you can't come in and tell that thread what to do. As we, again, mentioned in the previous video, you've got a single loop, if you will, a single function in here, say. And you imagine this is a single thread. So let's pretend we're the controller of this thread. And now here's our single infinite thread. So what we do here is say, process some UI, process event handlers, and this is super simple and not exactly how it happens, but you kind of get the point. Process external messages, and then go in this infinite loop. So what I'm kind of demonstrating here is, let's say this button was clicked. Well, when you click this button, it doesn't necessarily instantly and stop everything in the world and come straight into here. What happens when you click the button in here is that it goes to a dispatcher object and gets queued to be handled. And then the ultimate message pump of this window, the thing that is like this infinite loop that's simply handling all the messages from the system, goes in this loop and kind of says, right, handle these messages. And it's not this way because, like I say, the caller, when you click, pushes a specific event onto the queue, and this is more like a queue, dequeue, just in a simple pump, but it's not that simple. But if, in terms of understanding what's going on, you imagine this is a single thread and somebody else wants to talk to us. They can't come in anywhere because we're stuck in this infinite loop doing what we want to do only. And the only way they can talk to us is to say, right, this queue is going to read something. So this queue has, say, got a var. And again, this is not how it works, but this is a point of example. So let's pretend we just have a list. I don't know why I keep writing var and then the type of objects. Something wrong with them this morning. So this will be, say, message queue equals new list of objects, and this would be, say, your messages. And now in part of here, this, say, event handlers, blah blah blah, whatever we're doing, we would then say get var next message equals message queue dot first. And again, you wouldn't use a list, you'd use a stack or something else. This is purely demonstration. So let's even just go nastier and just get the first message. No error checking. Again, pseudocode just to kind of get a point across. So what we do is take the first message from the queue, or the oldest message in the queue, and then we'd say process the message. So you'd process next message, and that's at the point where now you'd handle what the message was, and you'd do something with it, and then you'd remove it from the queue, and then you carry on your loop, or you'd simply process all queued messages. So when we want to talk to this thread, our application, we'd have to get access to this message queue, tell it that we want to handle a button click because we've just been clicked, passing the info, and that goes into this message queue. And then at the point in time when this single thread decides that it's ready, so after it's done whatever it wants to do in excess to that or handled other messages, this message will eventually get read and pushed in. And that's kind of what's going on with the STA threads. And again, that's really not usable code and very poorly written. It's purely trying to visualize what's happening. So our window has one message pump, and you can actually see that in the Falsetto Word application. If you look at the window resizer code, you'll see that I've hooked into the message pump. So let me just pull that up for you so you can take a look. So as you can see here in the Falsetto Word source code on GitHub, in the source Falsetto Word window resizer source code, we have this window procedure. This is the message pump I'm talking about. And we can hook into it by going to the source initialized. We override the source initialized, or rather we hook into it there. And then when the window is initialized, we start using some COM interoperability here, or rather this isn't COM, but this is legacy code, getting the handle of the window like you used to do in C++, then getting a hwind, which again is a handle, again C++ stuff. If we get that handle, then we hook into effectively the message pump. So this is sort of, if you know C++, this will look very familiar. Otherwise, this will look completely foreign and you'll have no idea what's going on, but that doesn't matter. You don't need to know that. But this is that kind of message pump I'm talking about. So every single thing that happens in your window, in your WPF application, will get into here in terms of UI. So everything that happens on the UI, moving the mouse, drawing the window, clicking a stylus, minimizing, maximizing, you name it, they're all passed in this kind of message pump. And this is the window it's talking about, which is our window. Then the type of message, then some details about the message, and then whether it's been handled and shouldn't be processed by anyone else. So this is kind of the infinite loop, and I make use of that to do some low-level stuff to make our custom window work nicely and to monitor when things have moved and you're dragging and dropping a window. But this is the message pump I'm talking about. So that kind of gives you a visual of what the message pump is. And again, the reason the STA thread needs to happen, or rather how and why it needs to happen, is to pass messages into that message pump, because that's how all the other legacy code works, is through message pumps. So the way to communicate cross-platform, almost, if you will, between two applications, or a modern application like WPF and a legacy application like some XL API, is due to they need to match. They need to be able to communicate successfully to be able to make use of any old stuff that's on a Windows machine. So I'd say ultimately, as time goes on, that requirement will be removed because obviously there's only so far you want to keep real legacy code in some system. You want to modernize it, but that's where it is right now. So in terms of this message queue we're talking about, so now we're ready to say, right, a message needs to be queued to be handled. So let's start digging into actual source code and see where this happens. So the message queue handler, if you will, the thing that needs to receive messages from outside, or necessarily not even outside, inside your own application, but we want to tell it to process something on the UI, on the STA thread. That message queue handler is called the dispatcher. And basically its job is to queue up messages and dispatch them to the thread that it's linked to. So a dispatcher isn't necessarily specific to only STA threads and UI threads. A dispatcher is a generic mechanism and system that's in code. And if we look at, as I mentioned earlier in the video, the app overrides application, and the application is a dispatcher object, and a dispatcher object has a dispatcher on. So ultimately our app has a dispatcher, and then everything that's created, you'll notice then, let's have a look at the main window. You go to the window and you dig right deep down. You can dig down to any UI controller in WPF. Every single one, as you dig down, you'll end up getting to a UI element. And a UI element is a visual, and a visual is always a dependency object. And finally, a dependency object is ultimately a dispatcher object. So what that means is every single UI element, a window, a button, a text box, a list, everything is a dispatcher object. So every one of those will have a dispatcher so that we can queue up messages. So now if we have a button and we name the button so we can actually access it. So let's give it a name, my button, and you'll have seen this in the last video, but now it should make a bit more sense. Now you can do my button.dispatcher, and now from that dispatcher we can dispatch messages, and you'll see get as a dispatcher this dispatcher object is associated with, and we'll talk more about that after. But now you can see that's where our begin invoke and our invoke methods come from. So executes the specified action synchronously on the thread that the dispatcher is associated with. So what that means is the dispatcher is associated with the button. It will be linked to the thread that the button was created on. So therefore, any action that we run inside invoke will run on the thread that the button was created on. That's ultimately what that statement is saying. And that's how we jump back to the UI thread, as we mentioned in the last video. So the dispatcher is the thing that receives the messages to be queued, and then ultimately runs that code, or tells the thread that the dispatcher is linked to run that code. And as we've mentioned, the WPF app and the application is a dispatcher object, as well as every UI element being a dispatcher object as well. So let's take a look at this dispatcher object source code. So if we pull up the Windows-based source code on reference-source.microsoft.com, this is the dispatcher object, and this is the actual source code in the .NET 4.7.1 source code, if you will. We don't need to understand much about it, but the point I want to show is every UI element, including the window, the application, everything in WPF is inherent from one of these. So if we scroll down to the constructor of this object, which is here, you'll see that when it's created, so when the app's created, when the window's created, when the button's created, it will get the dispatcher, which is what we access, which is also a public property that can be accessed, which is visible on here somewhere. Well, that doesn't matter anyway. The dispatcher is as we've seen, accessible publicly. It's just not showing here because it's not directly a dispatcher object. You have to implement it and then expose it. But the point here is the underlying dispatcher, when you create the object, is a dispatcher.currentDispatcher. So if we take a look at dispatcher.currentDispatcher, then we have the get. So what happens here is it will say the current dispatcher is from the thread. So it jumps onto the thread obviously the current thread rather, where you're calling this. So at the point of creation, and this is why we say when you create a button, where you create the button, where you create the UI, is then locked in, that the dispatcher is linked to that, is because it then says, well, from thread. So you don't need to understand this code the way that it says from thread. You can take a quick look and we'll talk through it lightly, if you will. So you pass in the specific thread and you want to get a dispatcher. And what it first does is it says, right, the dispatcher is equal to a possible dispatcher target. If it's null or it's not on the same thread, then it means the dispatcher needs to be found. So it goes looking for it. If the dispatcher isn't equal to null, which means we found one, then if it's still alive, we found the dispatcher, and if not, we do that and it returns. So without getting into the depth of where these possible dispatchers are and where they get tracked, all this does is says if we're on a thread with thread ID of 1 and we call from thread and thread ID is 1, the dispatcher that we get returned, the thing that the actual dispatcher object that gets returned, is only ever created once per thread. So if we went further and further into the code, which there's no point because I'm telling you what's going on, you can dig deeper yourself. If we were to call current dispatcher or dispatcher from thread and we're on the same thread, every time we'll get the exact same object. If we don't, then a new one's created. So this is going to first try and find the dispatcher that has already been created on this thread. So if we've come in on thread ID 1 and we've called current dispatcher ever once, then that's a created instance. It will effectively be this instance that then gets passed in and is available. Otherwise, it will then create a new one. So I'm talking in a circle here really, but basically all you need to think about is if we call current dispatcher on the same thread, we will always get the same instance of the dispatcher. So every thread has one dispatcher, and that's all this current dispatcher does. It says, if there's already a dispatcher created for this thread, I'm going to return that instance. Otherwise, I'm going to create a new one for this new thread, and now anyone else on this thread requesting it will get that same instance. So it means that a dispatcher is hard-coded and linked to a single thread. And what that gives us is the ability to get a dispatcher that ultimately calls code onto the thread it was made on, a way to effectively send code to that thread. So when we created a new button, our dispatcher, for example, var button dispatcher equals my button dot dispatcher, var window dispatcher equals dispatcher, because we're on the window already, or if you want it to be slightly more obvious, you can do this dot dispatcher. But there's the two dispatchers. We can also say var get dispatcher, and that will equal where was it? Dispatcher will have to do the full namespace. So we're going to have to do, because the dispatcher object's the same name, we're going to have to do system.windows.threading.dispatcher to get the actual static instance. And we can now call from thread, the code we saw. And we can say thread.current thread. So we're going to manually call that ourselves as well, and we're going to get this dispatcher. So this dispatcher. And then on top of that, we're also going to say var new thread dispatcher equals, or rather, we'll just do dispatcher. And again, we're going to have to do the type, because this object has a dispatcher. So that's now going to be a new thread. And then we're going to do new thread dot start, or rather we're going to have to wait for it. So in fact, we don't have to wait for it. What we'll do, we'll get all these here, we'll start a new thread, and then we'll use them inside the new thread. So now we'll jump in here for new thread dispatcher. And this is really just proving the point and showing you what I mean to make sure you're aware. This will then be the same code. So we should have just done that. So now we'll get another dispatcher. A local parameter name new dispatcher that cannot be declared in the scope because the name is used. And then, oh, it's because we're in a thread. We want to put that. Well, in fact, we could just do a task here, but oh no, sorry, it's because we already got it declared there. So we set it there, makes no difference, we could have declared it inside here. In fact, why don't we just do that now? Change the way I'm thinking. So now we have 4 dispatchers, and then here we can now do a check. So what we'd say is if, and what I'll show is the button dispatcher equals the window dispatcher, and the button dispatcher also equals this dispatcher. So all those should be true. We should get into here. Then what we should also not do is if we say if it's a button dispatcher equals the new thread dispatcher, this should not be true. So we shouldn't get into here. So we run that code and we click the button. Then we should see that the way we've spoke through that code, you click the button, have a dispatcher for the button, which we have, one for the window, one for this, and then we'll get one for the new thread. And again, if you want to see the threads, you can click on the thread. You can see we're in thread ID 4 at the minute. And if we stepped back, we can't step backwards yet, but you would have seen this. In fact, let's restart that so you can see. Or rather, just step over that a minute and click the button again. Click it once more so I'm in the right part. So you can see at this point we're on thread 1. At this point we jump to thread 6 now. So we're on 2 different threads. So we have 4 dispatchers. All these 3 should be the same because this dispatcher is on the same thread as these were created. And these 2 were created on the same thread as well. And then we've purposely come off to a different thread and tried to get it for the current thread, which is ultimately what it does when you create a new dispatcher object. These should all be the same, so you get inside here correctly. This shouldn't be the same, which it isn't, and it jumps over. So the dispatcher you'll be getting whenever you're doing a dispatcher, all it really is doing is saying the current thread I'm on, so thread.currentThread, get me that thread, basically. So what that also means is if you're on a different thread, like in here, but then you want to call into the thread that a certain object you have access to was on, like the button, you could say inside of this thread, my button.dispatcher, and now you can push messages to it by saying invoke, and then you just pass in your action. So now code in here will run on the thread that this was created on, which we've shown before. So now let's do var a equals 10 or something, just to 109 because I've typoed, and we run this code, and again we'll inspect the threads window to see this happening. So here's the button, you click it, the dispatcher's on thread 1, we get into the new thread, so which was thread whatever number, we didn't stop there, let's just run this again. We're on thread 1 here, you get into the new thread, that's thread 5, but then you dispatch onto here, and you'll see now we're back onto thread 1 inside this specific call, so we jump back onto the thread that this was created on. And that's the dispatcher in action, that's what we use to jump back to the specific threads that, in this instance, UI was created on, and that's how you what's called jump back to the UI thread. So that's why you'll see all the solutions saying my button.dispatcher.invoke, or if you're inside a window, simply dispatcher.invoke, or if you're somewhere completely else in code, you'll see application.current, which gets the app. And then from that, it does dispatcher, which is doing nothing but getting the exact same dispatcher because this was created in the main function on the main thread here. So you'll get that, and then you'll see invoke. So hopefully now when you see solutions to the problem that I haven't even shown you, to be honest, let me show you the problem. New thread, and then we try to edit the button. And I'm jumping ahead a bit with what I want to explain, but just quickly to show you the error. Let's try and change some UI off the UI thread. We click the button, get into here, new thread, and then you're going to get this call. And this is typically the reason why everybody looks at what threads do. The calling thread cannot access the object because it was because a different thread owns it. And this call, we'll see the exact source code shortly of why that happens, and that's in order to simply stay strictly valid as an STA thread. So the code that the Microsoft wrote for this button and for all the UI. There's no reason why it can't edit the button text. The only reason it can't is because it has to adhere to STA thread principles, and that is why it then purposely throws that error to say that's not following our rules, if you will. And then when you get to the solution, you'll see why in a minute this is the solution. So hopefully you at least know what application.current.dispatcher is and where it's coming from. It's basically the apps application, which is a dispatcher object, which is a dispatcher, which is created when the app's created in main, which ultimately means you simply have a dispatcher that can link to the thread that this stuff was created on. So hopefully with all those explanations and this kind of layout and this quick test, you understand that a dispatcher is nothing more than an object you can call invoke on to run some code on the thread that the object it's from was created on, if that kind of tongue twister makes sense, but hopefully it should do. So let's dig into that button.content that we just did. So I'll just undo. Let's dig into the source code of this button.content, and you go here and you can't see the source code because it's in the DLL. So let's just jump online again and get to the source code of this object, and let's see what's happening. So you can see here, we've got a button. We search for content. I'm not going to find it that way because all the side menu here. Let's just scroll down and look for content. I should see it in a moment. In fact, I should find it by doing object content. Nope. Oh, sorry, you won't find it in button because button's a button base, and a button base is a content control, and the content comes from the content control. So a button is a content control. When we're doing .content, we're accessing that. And then in here, we should find the content property. So you'll see content property as a dependency property, which allows MVVM to work. But ultimately, the content is here that we're setting. And you can see that in the getter, it's fine. In the setter, we set value. So in set value, boils down to the dependency object, which is what everything inherits from. And now to set the value, it passes in the dependency property, which is the content we want to set, and the value. And the first thing it does is say, do not allow foreign thread access. Then if this is a no-op, if the object is not assigned dispatcher, but basically this calls verify access. If that passes, then it simply sets up the property change, queues it up, and then the property gets changed. You don't need to know how that works, but basically that means your content gets changed. But the first step you'll see here is verify access. And we click verify access, and you'll see what it does. It gets the dispatcher of effectively the caller. This is the button, if you will. So this is going to get the button's dispatcher, which is the thread it was created on. If the dispatcher isn't equal to null, if we have one, then, so basically if the button was created, then we should check. So if the dispatcher verify access call then says, if not check access, throw this exception. And this invalid operation exception, if you were to follow this down, is that message, the caller, you blah, 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 that every message we just saw. So the check access is a simple check. And you can see that this then simply says, is the thread equal to the current thread? So that means the thread of here, which is the dispatcher thread, which if you then follow the dispatcher thread, just for completeness, the dispatcher thread at the point of being created is the thread's current thread. So all it is when you create the object, it's the current thread. So the dispatcher thread is the current thread. So is the thread we're created on the same as the thread that's actually calling the request to change the content? So that boils down to in our code being, is this thread we're inside of, because it uses thread.currentThread, the same as this? So the check is basically saying, if my button.dispatcher.thread isn't equal to thread.currentThread, we'll get into here and complain. So if we put that check ourselves first, this is almost like a check, are we on the UI thread? And if we click the button, we should get into that if statement, because it isn't, which is the check it's doing for us. So we've detected here that we're not on the UI thread, if you will, we're not valid. But instead of us having to do that code all the time and do this check constantly, which in theory we should have to do, this will actually throw if there's an exception. So there's a bunch of helpers on the dispatcher for, or I say there isn't actually. There's helpers somewhere for if, see if I can find it. In fact, it might only be on Win Forms. I'm thinking of Win Forms, aren't I? So on the Win Forms one, there used to be a is invoke required kind of check, which is doing nothing more than that check we just wrote. But in terms of if you want to be safe and if you're doing things directly and you're working with other threads, then you can kind of just call dispatcher.invoke and do your work to make sure you're playing it safe. And there will be no harm if you're already on the same thread and you call invoke. You're going to do no harm. You're simply going to be out of sync with your code because this code doesn't run it, necessarily in sync. So the invoke should directly, because it'll call back and lock. But if you want to start doing async code, then you've got async, invoke async. So just keep an eye on if it states synchronous or asynchronous. If it's asynchronous, then it's going to run at the same time the same time as your thread. So if we changed this call to be asynchronous, you'll see that we should hit this breakpoint, and then we should hit this breakpoint because this gets queued up to be run on another thread. So you hit this first, and then after a while, it comes back and hits here. So just be aware if you're invoking on non-synchronous calls that the flow of code is not going to go 1, 2, 3, 4. It's potentially out of order. The invoke, though, does explicitly state it's synchronous, so it should lock, and effectively this should always hit before this and always complete before that. So that will hopefully explain the direct reason and where the error comes from in source code when you try to change, content off the UI thread and it complains that you can't. And that is, this call to check access, which is a call to verify access, which is called by set value, which is called by every item on a UI element that has, is a UI element. So in here, it's again the content property. So it's basically this object that they will all call get value, they'll all call set value, which will then all follow that same procedure. So you'll notice everything, the button.content and text.text and anything that's UI specific, you can go to any element, a specific one. Trying to think of a simple one. Let's go to text box base and do dependency object. What have we got? Something hopefully in here. I'm not going to show anything here, are we? Of course, you don't have a single object to show. That was a good example. And that's because control. Well, anyway, you get the point. There's everywhere. There's a, like there, for example, border brush property, border brush, set value. So you try to change a border brush, border thickness, set value. And like I said, this is hard coded in the source code. They've done that for the reason of making sure you don't alter these properties, because then once you do change the dependency property, this will bubble up through MVVM, if you will, to handle the notifications, and it makes sure all of the changes that come from iNotify property changed events are already run on the same thread by default. So that's why in the Faceta Word application, you don't see us having to do any dispatcher.invokes anywhere yet, because we're using MVVM. So when we bind a button property and we're using binding, the binding gets a set value which calls into the dependency property, and the dependency property handles getting back onto the right thread. So I think that's enough talking about the layout of what's happening, if you will. Now let's break down the application, the construction of the WPF application on a kind of lower level. So as you see, this main is created automatically, and that's going to do then Sta thread, and it's going to do all this for us. We can override this and create it ourselves. So at the very beginning of the application, as I mentioned, it compiles the app.xaml, or rather compile time, it compiles it. And it builds, because it's an application definition here, it compiles and creates that main function, which we can see right here. So if we change the build type of application definition to just page, so now the app's not going to generate a main. So if we compile now, it keeps telling us, because we've got this auto-generated code open, program does not contain a static main function suitable for entry point, because now you can see the main doesn't exist. And here's the compiled source. And that's because we changed that to page, which is fine. So now what we'll do instead is we'll make our own main function. So we'll do public static void, just like we saw. and main, and ta-da, our application should now run. So if we run this, it should compile successfully. It will refresh our auto-generated code, which can close now. You can see we get into the application, we finish, and it closes. So now our WPF application is nothing more than a blank function. So now we can do whatever we like. We can say do var file open dialog equals new file open dialog. Today would be nice. Or is it open file dialog? Do we always get back to front? Yep, it is. We do that, dot show. And we run this, and we now get, where's the pop-up disappeared? Well, for one, we haven't tagged this with what we need to, which may change the function of it. So force the Sta Thread attribute on there. And then now you can see it works. So without the Sta thread, when we were calling open file dialog, it failed to work. So you can see that again. We remove the Sta thread and run, and nothing happens. We're still running, but the problem is the open file dialog has no way to display a dialog for us because we're not an Sta thread, so it doesn't know how to communicate with us. So now you can see there's nothing's happening. The application's broken for the most part. And this is using built-in the .NET Framework library. We're using a function that shouldn't actually work. And the only reason it's working is thanks to this Sta thread. So once we honor this attribute, which we could dig into, but like I say, that's not kind of the point. You don't need to go that deep for understanding this point, is that your entry point to the application is nothing more than a public static void main for any application. Once you're in there, it simply runs from here to here, just like a console application does. It starts here, and once it gets to here, the application shuts down unless new threads were created here, new foreground threads. So this is our application now. And we've changed our entire WPF application to just open a file dialog, and that will only work when we have Sta thread. So that's kind of a proving point of our logic. So we can now happily say our thought was right, our investigation into code was right. And I always like to do this, whether I do it behind the scenes or live in a video. I've literally done this live in the video to prove my own thinking, if you will. That investigate the code, dig deep, understand. And then if you have an assumption, like I'm trying to preach here in this whole video, that this Sta thread is required for things to work that are calling, lower level stuff, it's okay saying that, but then you guys might be saying, well, no, that's not true. So it's always good to prove that what you're saying is right as well. So if we understand that the way that this should all work has to be an Sta thread, and that's in order for the message pump to work and blah, 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 then how do we prove it? So what we do is we find something in the .NET Core library, the .NET Framework library, that is quite clearly starting to have int pointers, hook procedures, things that look to us like, legacy code, and that's the point I'm saying Sta thread is to support legacy calls, and that's showing there. So by the same principle, if we were to do something that wasn't Sta thread, it wasn't legacy code specific, it should still work without the Sta thread. So what should still work here is if we mimic the original main function, which we can do var, 1 second, what was the new app, something like that, new app, and then we can do app.run, and this app.run we'll dig into. Let me find the source code for the app.run so we can see what that does. So here's the source code to the application. Here's the run. The run calls verify access, which is the same function to make sure we're on the right thread. So if we were that, in fact, let's prove that point then. So this verify access is the dispatcher object's verify access. So what that means, if we were to try to run, and the problem here is it's going to close instantly though. Oh no, the thread will be on a new foreground thread. So if we were to do, say, new thread, which will be a foreground thread, and to start it so the application won't close. And again, let's first prove that's the case. So we run this now. It'll create a new app, it'll start a new foreground thread, and mind you, that thread will finish. So we need to do, say, thread.sleep 5 seconds. So now the application should be in debug mode with the orange bar at the bottom. for 5 seconds. So you can see it's running and it's kept alive by this thread, and 5 seconds later it stops. So because we have a foreground thread, the first case is true, the application stays open. Now, if I'm understanding correctly, if we were to put this in here, app.run, we've created it on one thread and we've started it on another, and the run source code states that it'll do a verify access. So the first thing this should do is call that exact same error we saw before of the caller was created blah blah blah. So we're getting the exceptions, that's good. So we're understanding that if you create an app on one thread, it has to be then run on the other thread. And if you remember the original auto-generated main, it was obviously that case. It did app.new app.run. So if we were to do that now and run the application, the first thing that should happen is that the application actually runs. Now we get our window back and we get the button back. And in fact, that's not running because, oh yeah, so the point of that won't run because of the app is an application which is then trying to follow all of the STA stuff. So even this is hard tied to an STA thread. So I'm trying to think of something we can spin up that isn't STA thread related. Just to prove that, like I say, we could in theory run a WPF application without STA thread. We just need to simply find something that can run that isn't, reliant on that. Some part of the code that's not reliant. So I mean, one is obviously we can run, as we saw, simply a new thread that does nothing, that keeps the application alive. That's kind of the proof, almost in itself, that we are running an application, although we're not doing anything exciting. We have an application running, that then it does run, it does start, but we're not getting any kind of, graphical feedback to kind of show. So I think in terms of UI, obviously almost everything on Windows has been engineered that way, WPF, Win Forms. So we're going to struggle to find anything we can pop up on the screen without STA thread, because that's kind of all working in the same region. But I believe we could do it. We just simply have to make something that doesn't honor STA threads. So we have an STA thread that we know is a requirement now to be a valid application, if you will. We can then call, hopefully, just create a new app and run the app. And that should now run our dialog. And we still don't get the dialog. So let's take a look at why that is. Let's first change this to just say 2. Change back the compile of this to app definition, and let's take a look at the original code. We didn't initialize components, the key step there. In fact, that might have been the key to working without STA threads. So chuck that back in, get rid of that, change that back to page. So now it's not auto-generated. And now we should run and see the application first, which it does down here. So now let's try my original theory of removing the STA thread, which, to be honest, I think it'll still spin up. No. So now it's complaining the calling thread must be STA because many UI components require this. So we've got a forceful thing inside of the main window, and the window's now baked that check. So if we went and looked at the source code of window, we'll find that it's doing that kind of check. So if we were to go to window, might as well look at it for completeness. Like I say, I'm doing this live, so I genuinely am, seeing this happen as we're doing it. So that's the static constructor, is the public constructor. Demand or manage code is trusted window is false. Initialize. Bypass layout policy true. Is inside app true. And then there we go. If it's the dispatcher, add it to the internal windows, set up the window. Otherwise, non-app windows add. So I actually don't see any, unless there's a check in here. I actually don't see any error there with the, I can see it's doing a check, but I can't see anywhere it's throwing the exception in the initialize, which is interesting. And that's the complete constructor. So I'm actually not sure where that error is thrown from, basically. Unless I am on the wrong place here. Let's see where it's being called from. Oh, where's it gone? So let's take a quick look at where it's coming from. The constructor of input manager. So this isn't actually coming from the window constructor, this is coming from the controls in so this is coming from the controls inside of the initialize. Close that down. So this call is bubbling a bit further down, so it's going into the initialize components. So if we were to break here, I thought it broke before though. Oh no, it's breaking there. But internally, this is going into a constructor of the main window into there, which we see, but then it's going into creating a control inside the window constructor. But I don't see inside of the window, unless I'm overlooking something here. Main window, system.windows.window. Am I in the wrong source code? I might well be in the wrong source code here. We are in system.window. No, I'm in the right one. So that's actually quite interesting. I mean, we don't need to dig into this. I'm just getting a bit curious now as to where this is actually throwing the error. Where I understood it if we went into initialize components and it creates a control and the control does the check. But the... Oh, hang on. Was it a private? Am I overlooking something silly here? Was that a private constructor? The window control framework get current input, keyboard navigation. So it's this. I'm trying to find this line here. We've gone into the constructor of the window, but then somehow it's started creating controls before we've gone into the initialized components. So purely curious here. Like I say, this is nothing specific you have to understand. It will be a window call though. So what might be happening actually is there might be a message pump already going on with the window that's firing an event, or hang on, is it just a static creation that's starting because we're accessing the window in general? But I don't think so. We haven't accessed anything static. So in fact, that we are registering handles here that register when things happen. So one of these might well be the created event that gets fired when we are created somewhere. So my guess is one of these static calls is being fired, which is then starting the creation or the check, the setup of the window. So we've got event manager, register class of the window, manipulation event. I can't see anything off the top of my head though. I can't actually see the reason why here, unless it goes into there, but we haven't seen a step in. So for now, I'll leave this one as something if you guys want to dig into the source code and find for me. But bottom line is we still can't create even the main window because of obviously the checks that are happening. It's a valid check. I just wanted to try and get around that to, dig a bit deeper into the confirmation. But no, we can't run a WPF application's UI without Sta thread because obviously rightly it's enforcing that. But we can run a WPF application in the sense of we don't create an app, we simply make our own code here. And even though it's compiled as a WPF application, we could do whatever we wanted here. It doesn't have to be. The Sta thread requirement comes about due to, that whole restriction and the requirement to follow those sort of guidelines, if you will, and the rules. So what we've now got is a replacement. So we've changed this to a page. So there's no auto-generated main. We've now made our own main, so we're in control of it. And we've repeated what the original code did, which is a new app, initialize components, and run. So now we're in control of this. So we now know what the application does. It comes into main, it creates the app, which we know creates the dispatcher object and all the threads and stuff. Initialize components is then, we could dig deeper, but basically that reads the XAML file, figures out, what to create, like all the window and the buttons and things. And then the run, we'll take a look at now what happens in the actual, the run code of the application. And as I mentioned, we know that the minute this code returns, the application would end. So we know that this run must basically show the window, and when the window's closed, it must return, and until then, it doesn't. So back to the application source code where we started, and then I got a bit lost in wanting to dig deeper. We go to run, we do the verify access. which checks for the thread being on the right thread, which we proved. In browser hosted, we don't care about. So basically, it'll run internal. So the run internal verifies access again. Some stuff we don't care about. So we scroll down. If the app's in shutdown, we complain. If the window isn't equal to null, which it is in our case, so we ignore that. Ensure we have hwind, and then if hosted that. So basically, that would do nothing. So ensure hwind source, callback. There's no kind of lock here. So what this would do is, or what this must do, is start a message pump somewhere that starts a thread that's in the foreground in order to keep it alive, because this doesn't actually lock the thread as such. This is like done and dusted, if you will. It comes in and says run, it verifies access. If the window isn't equal to null, but if we've seen it is, it's null, so this won't run. Just simply ensures the hwind and does that. So what must be happening is at the point of creating the application, a dispatcher object inadvertently creates a dispatcher by doing current dispatcher. And the current dispatcher would create a new dispatcher if it didn't exist, which then adds a reference, does all this lot. Message only hit. So here we go. So this is now the bit that starts a message pump. So a message pump will then run and process messages on a foreground thread, basically. And it will create a hook, which will then be the hwind. And you can see here, look what we have. This is the thing in the Faceta Word application I overwrote. And this is kind of the message pump that starts. So in the dispatcher's constructor, let's have a look at what happens. So we are in static constructor. No, we want private constructor. So look over here, we've got so it's a private constructor only. We get references to the thread as we know, and here's something I recognize. So what we're doing here is creating a new synchronization context. So a synchronization context, without going too far into this, stores the current thread and starts a message pump. And I know this from when I used to do C++ work, so it's a new thing, but I know what this is going to be doing, the point of it. So it's going to start a new message pump ready to process messages. And the synchronization context is a whole other thing, but I don't feel it's worth talking about, in this context. We'd be doing too much in this one video if we did that. So I want to try and find the key point though, where the message pump starts, if you will, to kind of show you what keeps the application alive. So we go backwards. Where are we? Hwind. So we hooked into this. We process messages here. It's not in there. Backwards again. Current dispatcher, new dispatcher, internal. So let's get back to the private thread. So we have this, we handle exceptions, create the synchronization context, create the window, window.value. So a window is a message only wrapper. So this is what's handling it, and then we add a hook to the hwind wrapper. Now, so I think what I'm doing here is digging a bit too deep for, I could explain this, but we're going to waste a lot of time. So what I wanted to show is that the run call of the this call here is what's then locking the application, and it does that ultimately, as I say, by starting a message pump that stays alive. And what will happen is that we will have, once this application run starts, it will push the initial message onto the message pump. So when you make a new app, it will make a new dispatcher. The dispatcher will instantly start its own message pump, if you're ready to process, but a message pump won't start until at least one message is pushed on it, so nothing will happen. So when we call run, it will start that message pump kicking, and now the application won't end until that message pump dies. And then after that point, once it's running, it can then go and start up and create the window, display the window, and hook into the Windows close event, and when the window closes, it ends the message pump, and then therefore it returns here. But looking at the source code, I haven't, I'm digging into it as we speak. It's going to take me probably 20 minutes to dig around, and I don't want to do a video when you're just watching me dig around source code to try and find, that little bit of code. In fact, if we look here, I just had to pause the video and do a quick look because it was going to drive me nuts otherwise. What I overlooked was when we do window.run, or rather app.run, and here we do this.run, which takes us to here. We do run internal, which takes us to here. And we do in here, I'm going to forget where it was again. This check I overlooked. The invoke dispatcher, if we're not in the browser, I overlooked because I thought it was in browser. If we're not in browser, it calls run dispatcher. Run dispatcher then finds the dispatcher, calls run. And then ultimately the run finally calls what I was looking for as push frame. And this push frame simply chucks a message onto push implementation, which goes to the synchronization context we created, which ultimately pushes a message onto the queue, if you will. So all this you don't need to fully understand, but what's happening, the thing that keeps the whole application alive, is that when you call app.run, it calls the dispatcher.run, which pushes a frame onto the dispatcher message pump, and that's what then starts your whole dispatcher from running, or rather starts it running, and that's what keeps your application alive. So it might be a little bit too much detail there, but I wanted to try and show that for completeness if anyone wants to dig deeper. So like I said, now the application started, and the run method in the application checks if we pass in a window. But we saw it doesn't. It then sets up the main window and all the internal properties of that window. So if we went back a few steps, back up, you can see this run internal basically does a bunch of checks. Checks if we have an item, adds it to Windows internals. And then what it does, interestingly, the thing that starts the window, if it's not visible, the run says, right, dispatcher, as we mentioned, begin invoke. So it pushes it onto the message pump that doesn't run yet because it runs here. It pushes the window on and says, if we're not visible, okay, send a message. And then this is the message here, the call. So ultimately, this little bit of code wants to run on the dispatcher's priority. So the dispatcher will decide when it processes this message, as we mentioned, that message loop. And then eventually it would do, here's a new window, show the window, and then return null. And that's the message that's going to go into the message pump. So the first message will be, well, not necessarily the first message. This will be put on the queue. The run dispatcher will add that blank frame to simply start the process. That will spin up, start the process. And then the only message left on the queue already is to show the window. Then the window.show is what then locks the application from closing because it doesn't return until it's closed, sort of thing. So that's the ultimate process that's happening. And you can go deeper from there. What I'm trying to do is give you enough information that if you want to keep digging, you should be able to really figure out everything from it. But the main point of what I wanted to cover here was kind of the STA thread, how the dispatcher is working, where it's coming from. So that's what's happening in the startup, and hopefully you understand enough that you kind of really, now that this application starts, it runs here to here to here, it hangs here due to the dispatcher, keeping the message pump alive, which then opens the window for you. When the window closes, the show returns, that message ends, and the application finishes. And we've overridden how the application starts to do that. I think that's enough of that. I'll briefly touch on the synchronization context that you will have seen being created when we created the dispatcher object. See if I can go back to dispatcher anywhere. Dispatcher object, dispatcher. Then when we got the current dispatcher, new dispatcher, we saw in here the synchronization context. So just a really brief 2-sentence thing about the synchronization context. So basically, the dispatcher is really very specific to implementing the STA model for like WPF Win Forms and things like that. And it's got a very specific model to follow and very specific requirements. So that isn't good for obviously cross-platform and future growth. So to kind of start separation of the dispatcher, if you will, so you don't have to start referencing dispatcher, you want to start referencing and using synchronization context, if you will. And the synchronization context is there to not necessarily replace the dispatcher, but be more cross-platform, if you will. So I may do a future video on the synchronization context, but ultimately you can use synchronization context if you use it correctly and not have to reference dispatcher. And then the synchronization context, if we go to this, you'll see the synchronization context boils down to a class that doesn't inherit from anything. So there's no tie to that. And if we look through the code briefly, you'll kind of see there's no, well, I say look through the code, it won't make much sense unless you know how STA works, like in a lot more detail. But what I can tell you is this code doesn't specifically get stuck or follow any routine that is STA specific. It purely handles synchronization of messages, but in a more cross-platform way. So that's what this synchronization context is about if you kind of see it in code. But again, that would take a whole new video to talk through. So this has been kind of a very detailed, very specific video, and this knowledge is really just there so you understand more about what's going on in the application, and you really understand ultimately just one error, which is why you need to run code that edits the UI on a UI thread. So it's kind of the only purpose of all this video is that you've now got a lot of background knowledge. You feel more comfortable in really understanding where that error come from, and in your code now you're more comfortable, and you should know when you're typing mybutton.dispatcher or dispatcher, or you're getting a dispatcher from a thread, or you're spinning a new thread up and you're invoking, that you feel comfortable knowing this isn't just a thing that's called .dispatcher or where's it come from, anything. Now you should understand exactly what happened. So this dispatcher got created when I made my button, and the invoke will jump back onto the thread that the dispatcher was created on and run, here. And that's really the key point, is to know deeply and fully exactly where this dispatcher comes from, as well as why calling like mybutton.content equals something else on a thread that isn't the creator throws an error. And the reason is because it wants to honor the STA thread, and then ultimately being able to spin up the application manually. So not anything exactly constructive in this video, but mainly just knowledge that I feel is very important to stop you ever being confused or not understanding being able to get a thread to run on a UI thread. So hopefully this video was useful. It's been different than some others. This has really been a very technical and kind of digging into source code style video. But if you found it useful and you want to support me, I do have a Patreon page, patreon.com/angel6. I'll put the link in the description. Any comments or questions on the video, just post a comment and I'll get back to all of them. And hopefully this video has been useful.